Okay. So, I like this topic, obviously. So we are going to take PV is equal to nRT. We're going to use that, what we know about gases, and we're going to mix it with the stoichiometry of a balanced chemical equation. And so there we go. There is our first gas problem with stoichiometry. So what I'm going to do actually, and it's going to look a little rough, so just bear with me,
It's like trying underneath each of these to see what we know. So, for instance, kind of dissecting it, notice that we have one gas of interest and we have one solid of interest. Oops. That's right. Okay, so under the gas, I'm going to start writing P. Oh, wow, I don't think I'm going to be able to do this. Let's do this. Under the gas, I could. I would write P, P, and D.
And actually, I think so. I'm going to write this here. And tells me some more things about the H2 gas. It says that its temperature of 22 degrees Celsius. I'm going to put an arrow to Kelvin. Got to fix that. And it goes ahead and gives us that the pressure of the H2 gas is 1.00 atmospheres. That's cool. That's in units, that pressure that we're good with using our ideal gas law constant. Okay. Can be produced. I'm going to go ahead and circle this N right here because we weren't given N, but hold that thought. Because it goes ahead and it says that with regard to zinc, we have 2.50 grams of zinc. Okay, I'm going to go ahead and put in the coefficients of 1 and 1. Okay, I know that I haven't written the complete reaction up there. Okay, so basically this is one of these stepwise. Do you see where we can use the mass, of zinc and its molar mass to get to moles of zinc? I'll just put moles of zinc, I'll put N sub Zn. How's that? Moles of zinc. Okay, and step 2, we can use stoichiometry. I'll just put stoich for stoichiometry. To get to, I'll put an arrow, moles of H2. Then we have several of these. That's how this one comes out. And sometimes there's more than one way to see this test. And that's just up to me to grade your papers and kind of feel how you did it. Sometimes I'll do it different ways, depending on what kind of mood I'm in. Okay, but this is the step. Use the mass of zinc, which is 2.50 grams. Look up on the periodic table what the mole mass of zinc is. You round it to 3 sig figs. This actually then, 0.0382 moles of zinc is what we're going to use with stoichiometry to get a mole of H2. One of the boring stoichiometry relationships, cold sun of 295 kelvins was going to appear in our equation. So, I like what I'm seeing with your homework. Just make sure you include units, like I've included units in here, with moles and our temperature on top. Pressure in the bottom.
While you're drawing that, I'll cancel some units. Of course, units and moles. It's my favorite part of working problems, factor label. Units of Kelvin cancel. Units of atmosphere cancel. And units of liters are what we're left with, which is awesome. And notice in this case, I've rounded to 3 significant figures because that's what I was allowed in both the mole term, the temperature term, and the pressure term. 3 things. So that was a gas calculation. Cool. Let's do another one. And I think I'm going to kind of do the same thing if you're all right with that. I just kind of lift from the problem
And then after I look at the problem, I'm like, oh, okay, I can handle that. Okay.
So in this case, we're dealing with we're curious about one of them is Q T9 Kelvin, and it gives me the pressure of H2 in atmospheres. Wow, 783 atmospheres. No conversion needed there. Okay.
Then it gives me some information about my ammonia. It says down here, how liters of ammonia, so next to my volume for ammonia, I'm going to put question mark volume, how many liters of ammonia can be measured at standard temperature and pressure. So this is where you're going to have to remember, we said standard pressure is 1 atmosphere. I'll go ahead and give it 3 sig figs, 1.00 atmosphere. And standard temperature is 0 Kelvin, which is 273.15, but I'll just go with 3 sig figs, 273 Kelvin. Cool. So I'm going to put a circle here under the moles of NH3. Don't know it yet. But do you see where we can start here? We can get moles. I'll put N of H2 using PV is equal to nRT. Not too bad. We can do that. And once we have that, we're going to use stoichiometry to get to moles of N sub NH3. That's awesome. Okay, and then we have 3 unknowns in PV and nRT that can solve for all of them.
So 3 solve for P of H2. Is it? It's plugging in what we know about the hydrogen. Pressure of the hydrogen, 0.783 atmospheres. Volume of the hydrogen, 125 liters. I know gas law constant, 0.082058 liters atmospheres per mole Kelvin. Temperature of the hydrogen, 290.
Rounding to 3 sig figs, you'll get 4.00 moles. Now we've got a little more interesting stoichiometry. It's not 1-to-1. So now we use the coefficients in front of the H2 and the NH3, which are 2 and 3. 2 moles of NH3 are formed for every 3 moles of H2 that we add. The middle term is the stoichiometric ratio from the balanced equation. So now we know this number here. Now we know that the moles of NH3 are 2.67. So now we're ready to use V is equal to nRT to get to the volume. Oh, that's right. Okay. So that's how I would do it, honestly. In fact, you see, I added this to my notes. I'm going to show you one other way. The fact that the product, NH3, is at standard temperature and pressure means that we can use this little relationship, which I don't always remember. Okay? Remember on part 1, we said that if you have, for every 1 mole of gas at standard temperature and pressure, which is what this is, for every 1 mole, okay, it is going to occupy a volume of 22.414 liters. You can use that as a conversion factor to knock this out. I know. So either way, I usually don't remember this, but the way this looks is like this. So we know that we're going to have 2.67 moles of ammonia produced. Okay? And we're at the volume. And so the fact that it's at standard temperature and pressure, we can use this relationship. 22.414 liters of gas.
Temperature of mole. Same equation, a little bit different. Or the same reaction, different different information given, different thing we're after. So, taking a look at this.
So with regard to the hydrogen, we have volume and temperature and pressure. Okay, again, excess nitrogen. Okay, so that's good. Let's see. Volume, 25.0 liters. Temperature, we're going to have to fix that, aren't we? 25.0 degrees Celsius. We're going to have to go to Kelvin. Pressure of hydrogen is 1.25 atmospheres. Of course, moles isn't given, but we could get to moles. And then again, nitrogen is in excess, and we're after something about the product. Okay, I'm just going to put V is equal to how many liters? V question mark in liters. Okay, and notice the big thing here is that temperature is 25.0 degrees Celsius. These are equal. That's significant. Other thing is the pressure is equal. That doesn't always happen. I'm going to put N is equal to, I'm going to put a circle there. We aren't given the number, we aren't given the moles. Okay.
So I had something to see. I thought, oh yeah, the only I had was the
Question that if you have same pressure and temperature, which we do, then he said, and he's right, that your volume will change relative to the number of moles of gas you have there. Same pressure, same temperature. Since that's the case, honestly, we can use the stoichiometry. Was this a? Thank you. 32, thanks. Oops. Thank you. Okay. You can use the relative moles. Okay, that's basically no ball. Bayhammer. Okay. 3 moles of hydrogen, 2 moles of ammonia. 3 liters of hydrogen, liters of ammonia. That's what that means. So here's how you can work this problem. We can take this volume, which is 25.0 liters, put it over 1, and then slide in that ratio on the previous slide. 25.0 liters of HM1 times 2 liters of ammonia liters of energy over that 7 liters. Now, here's the deal. If you forget that Avogadro's relationship, and you probably will have time on your final or whatever, do you see where you can actually do the process we've been doing? You can knock out moles, okay? Use stoichiometry to get to moles of this. Okay, then you can use PV equals nRT again to get to volume of this. You can. Okay? So, no worries there. So here's a caution. You can't just automatically say that the volumes are proportional the same way as the stoichiometric coefficients are proportional. You can, but it's wrong. All right. Okay, so here's where the fun begins. It's not really fun. Well, it is fun. I'm going to go ahead and